Hi, this is David Gibson. I haven't done a video in a while, but today's topic is PFT. Now, my target audience for this lecture is new students or anyone who needs basic information about pulmonary function testing. My objective is that you'll be able to interpret PFTs to some degree, or at least put them into 4 categories. And we'll talk about what those categories are in a little bit. But I'll get started with my slides. Pulmonary function testing fits into a category of diagnostics, pulmonary diagnostics. And I hope you can see this well. Top of the slide gets cut off a little bit, that's okay. Hopefully you have a handout that has these slides on them if you don't see me. The type of diagnostic tests that are commonly performed by a respiratory therapist are pulmonary function tests, arterial blood gases, and other pulmonary diagnostic tests not performed by respiratory therapists are things like VQ scan and other kind of radiologic procedures. Today, we're talking about pulmonary function testing. Forgive the animation. Pulmonary function testing is often confused with spirometry, but really they're 2 different things, or they're not. Spirometry is part of pulmonary function testing. In fact, pulmonary function testing is 4 distinct areas. One is lung volumes and capacities. We'll talk about that in this video, and spirometry. In the second video, we'll talk about interpretation of spirometry, and in the third video, we'll talk about FRC determination and diffusion capacity, the other pulmonary function tests. So there's the 4 pulmonary function tests. Today, we're going to talk about all of those, and to start out with, we're going to talk about lung volumes. Now, this slide, I would recommend that you commit this to memory and be able to draw it just like this. In fact, if you're taking an NBRC exam for respiratory care testing, as soon as they let you bring scratch paper in and a pencil, and as soon as you sit down to take your test, I would pull this out of your memory and draw it on your paper, because there's going to be several questions regarding this, and as I go through, I'll mention some of those types of questions. As you can see right here, I show a spirogram, and this is a patient that you're asking to breathe normally, and so you can see your volume on the y-axis here and time on the x-axis, and you might ask your patient who you're doing lung volumes on to breathe normally, and so you see this normal tidal volume here. The normal tidal volume is typically 500 cc's or half a liter. Then you can ask the patient to breathe in as deep as they can to completely fill their lungs. At that point, they're at total lung capacity. They've breathed in not only their tidal volume, but their inspiratory reserve volume. The inspiratory reserve volume normally is about 3,100. Then we typically ask the patient to blow all their air out. And there's 2 ways to do this, either a slow vital capacity or a forced vital capacity, which we'll talk about in a minute. If they blow all their air out till their lungs are completely empty, then they've blown out their IRV, their tidal volume, and their expiratory reserve volume. Expiratory reserve volume is 1,200, and they're at residual volume now. Residual volume, the definition of that is air that is in the lungs that can't be blown out, but it's air that remains in the lungs after you've blown out all the possible air that you can. When we do measurements, we measure at this point the FRC, and if we want to obtain the RV, we have this reading ERV from the lung volume test. We can just subtract the ERV from the RV, or I'm sorry, subtract the ERV from FRC. One thing I didn't mention, in addition to each of these volumes, you can group volumes together to form what's called capacities. And the two of these together are FRC, or functional residual capacity. There's these two above it combined is the inspiratory capacity, and I'll show you some of the values for these. All of them together, total lung capacity, the usable amount of air in the lungs, or the amount of air that you can blow out from a deepest breath, is known as the vital capacity, and that's what we're measuring in spirometry. Here's another look at it. This time, a graphic right out of the book, and it shows you the different compartments. Define the inspiratory reserve volume of 3,100, tidal volume of 500 or half a liter. Expiratory reserve volume is 1,200 milliliters, and the residual volume is 1,200 milliliters. Together, 2,400. The lung capacities, the inspiratory capacity, which is made up of the tidal volume and the inspiratory reserve volume. There's a test question for you, and it'll say the IC is made up of what two volumes? And the two volumes are tidal volume and inspiratory reserve volume. It's often done when you're doing an incentive spirometer. That's what you're measuring. The vital capacity is a combination of three volumes: inspiratory reserve volume, tidal volume, and expiratory reserve volume. And that's the usable amount of air in the lungs. That's the air that you can blow out. The FRC is made up of the two volumes: inspiratory reserve volume, expiratory reserve volume and residual volume, and that comes out to about 2,400. And then there's total lung capacity, which is the whole thing, including residual volume, 6,000. Here's another question that they might throw at you on the MBRC exam. They'll say, which of the following of the capacities can be measured directly? And the answer is the inspiratory capacity can be measured directly, the vital capacity can be measured directly. The FRC cannot be measured directly because you can't measure the residual volume directly. There's an indirect way to do it. We'll talk about that near the end or on the third video. The FRC cannot be measured directly, nor can the total lung capacity, because they both contain residual volume. You can't blow it out, so you can't measure it directly. There is an indirect way to measure it, though. A couple of important terms that you should be aware of. BTPS, which stands for body temperature, pressure, ambient pressure, and saturated with moisture. So that's when we blow air out of our lungs into a spirometer, it's at BTPS, body temperature, pressure, saturated. ATPS stands for ambient temperature or room temperature, pressure, normal pressure, and saturated. And ATPD is ambient temperature, pressure, dry. So when we blow out air, it's at BTPS. Then it enters the room, it becomes ATPS. So what's the difference? Well, if you remember Boyle's law, air volume, as air cools, the volume's going to go down. So as you blow it out, you'll actually measure less air than what was actually in there to start, because the air cooled down on the way out as it changed from body temperature 37 degrees to ambient temperature or room temperature. It cooled down, and Boyle's law says that air is going to shrink some. So most machines will extrapolate back to BTPS. It'll add a little extra volume to make up for the fact that the air shrunk some. So, and that's what this says. It cools from body temperature to room air. I say Charles' law, and that is correct. It's not Boyle's law. Boyle's law is pressure and volume. Charles' law is volume and temperature. So I'm glad I saw that, so I didn't tell you wrong. Vital capacity. The VC is decreased in restrictive disease, and it's a disease of low compliance. And what is compliance? I just want to review. That's really not part of pulmonary function testing compliance. You talk about that more when you talk about patients on the ventilator and whether their lungs are stretchy or not. But I want to review what compliance is. Compliance is a volume, in this case, tidal volume or more, divided by 20. For example, if you used a tidal volume of 1,000, we'd never do that nowadays. You know, the most tidal volume we pretty much use nowadays is 500, but when this slide was created, it was routine to have tidal volumes of 1,000. Of course, back then, we weren't as focused on inspiratory pressures as we are now. But if you did have 1,000 and you measured 20 of pressure, you'd have 50 of compliance, which is normal. Anything above, say 30, 35, 40, normal compliance. And if you had a tidal volume of 800 and you measured a high pressure of 40, your compliance would only be 20, which is kind of a poor compliance, bad compliance. So there's compliance. So let's talk about spirometry. What is it? Spirometry is a forced expiratory vital capacity. So we're going to measure that vital capacity on maximum effort. The amount of air the patient blows out in the first second is very important, and the FEC is timed so that, and graphed. And let's talk about that a little more. In order to meet American Thoracic Society standards, one must blow out for 6 seconds or obvious plateau, no coughs, starts and stops, good start of test, although the computer can back extrapolate. 3 efforts. When you're doing a forced vital capacity, you want to do 3 efforts with at least 2 of the efforts being 200 ml apart for consistency's sake. And the patient is assigned predicted values based on their sex, age, height, weight, and even race. All right, here's a spirogram. Watch the dot. This will be, we'll do a vital capacity. I ask the patient to start breathing normally. Okay, now, okay, breathe in, out, breathe in deep, 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 deep as you can go, and then you'll instruct the patient to force it out as fast and hard as they can. And that's their forced vital capacity, and then go back to normal breathing. So what we're doing is we're going to take this forced vital capacity here, flip it over, and represent it by itself, like this. So that's the forced vital capacity from the deepest point, from the maximum amount of air that they could breathe in, their total lung capacity, and blow out all the air. Of course, there's still air that they didn't blow out, the residual volume, but we're not worried about that right now. We're just worried about how could they empty their lungs of all their air and how quickly could they do it. And so, first thing we want to know is what was their FVC? How much air did they blow out? So here's the FVC here. This would be volume along this axis, and we could just read off the forced vital capacity, or the total they blew out. And then at 1 second, we'll draw a line. And wherever their curve crosses that line, well, this is the amount of air that they could, of their total, the amount of their total that they could blow out in the first second. That's called FEV1, forced expiratory volume at 1 second. So here's a little bit of information about FEV1. It's the first major timing mark, measured in milliliters. Like FVC represents the amount of air blown out the first second of the FVC maneuver. By itself is a non-specific value, since it can be low in both restrictive and obstructive diseases. FEV1 divided by FVC is another major value that we look at. And what is that? That's taking the FEV1 and dividing it by the FVC. So basically, this gives a percentage of how much the patient, how much of their air they could blow out in the first second. And expresses it as a percentage. Generally, high percentages on this are good. This is the first, what we call a flow, an indicator of flow rate. And if the number is high or the percentage is high, then the flow rate is good, means they were able to empty their lungs very quickly and blow most of their air out in the first second. If the percentage is low, then we consider that a low flow and the patient might have obstructive disease. So here's an example. In this one that we did, we had a FVC of 4 liters. FEV1 is 3.8, so if we divide the two, it's 95%. So the question is this good or bad? Well, absolutely it's good. What is good? Above 75% generally. Really below 70% is when you're talking about pathology. Here's another value, an indicator of flow, how the flow is coming out. This indicates the flow in the middle half, or the small airways, and it's derived, I won't really get into how the FEC, FEV, or FEF 2575 is derived, because you really don't need to know that. It's important to understand how the FEF 2575 is significant, but it's not necessary to understand how it was derived. And I do have a slide showing how it's derived by taking, splitting the FVC up into 4 parts and taking the 25% mark and the 75% mark, drawing a line between the two, and then mathematically taking the slope of the line. Don't really need to know all that, but just realize that this value represents air in the small airways, and it's really the most sensitive indicator and usually the first thing to show a problem when there is some reactive airways disease. There's also peak flow that can also be derived from spirometry. It's derived much in the same way 2575 is, only using the first half of the flow. And it roughly indicates air in the larger airways. It's easy to perform. Our patients are asthmatic patients that have routine treatments at home. Will often use a handheld peak flow meter that only measures this to kind of know where they are as far as their breathing that day. Next slide. Some of the other marks, 200 to 1200 FEV2 and FE3, we're not going to talk about those. They're not really all that significant, but just realize that these are also some more indicators of flow, like FEV1 divided by FVC and FEF or FEV 2575. The next topic is classification of spirometry based on disease process, and that's going to be in the next video, so go to PFT2.